Good evening. This is Sammy Shina. I'm the instructor of the Mechanical 5710 in-class section 201 for quality engineering. I've been teaching this course for quite a while, and I'd like to introduce myself for the first session for the course. So I've been working in quality for a long time. I have really spent a lot of time investigating some of the quality issues. I've consulted on quality. I'm fairly expert in all aspects of quality. I teach two other courses. One of them is Industrial Design of Experiment. The course is Mechanical 5750. And that I teach online and also in class. I teach it mostly in the fall, and I'll be teaching it next spring, next year as well. The other course I teach is Engineering Project Management, which is essentially a compendium of my experience as a consultant in management. So I've been working in quality at different companies, and I got interested in design of experiments and Six Sigma very early in my career. And as I came to the university, I continued my research and my practice of these professions. So before I started the session tonight, I wanted to kind of give you a little bit of a perspective, my own perspective, because I know a lot of the people that were founders of Six Sigma, founders of great quality ideas. And I wanted to give you a historical perspective before we get into the course. I'll try to be as quick as I can. So quality really started in early or pre-World War II, something in the 1930s. As the country became obvious to the country that we are going to go to war, the Department of Defense in the 1930s and 40s decided that for every part or every car they buy or every tank or every plane, there would be two suppliers. And the idea of two suppliers, if there's a problem in one supplier, the other supplier would come in. So before then, companies in the US were vertically integrated. So for instance, Ford, that made cars, would make all the parts for their cars. They would actually go down as far as owning iron mines and owning coal mines, and then making the steel, and then shaping the steel into the bodies of the car. So they really went all the way into the supply chain. So the idea, these monopolies wanted to control quality internally. So their objective was to control quality through the corporation. When World War II started, there was a need for supply chain. The idea that every major part in your product had to have two suppliers in case one goes bad. So that created the idea of supplier to company relationship and created the idea of inspection, monitoring quality, what to do with their rejects, things like that. So the largest company at that time, kind of the Facebook of its day or the Amazon of its day, was AT&T, the phone company. The phone was the way of communicating those days. So they decided that they needed a quality system to kind of maintain quality within their factories and between themselves and their suppliers. So they had an engineer work there by the name of Schuhart. So Schuhart was one of the originators of quality, one of the giants of quality. And he came up with the idea of incoming inspection, the idea of control charts. These are the kind of things we're going to talk about in this course. So they're about almost 100 years old. The next person that came out in that chain was Deming. So Deming was a disciple of Schuhart. And he came up with this idea, what we call DEMIAC, Design Act it's a cycle of quality, and we'll have a lecture on that later in this semester. I have a recording of one of my students that ended up working in quality in one of the major drug companies, and she gave a nice lecture, which I recorded, about this MECH system, which is an idea of enhancing quality by plan, do, act, and that's the acronyms that go into that. So what happened then is we won the war in World War II. So we decided that, hey, all these systems that we created, we don't need because we won the war and we're the best. So at that time, Japan was the vanquished country, and they appointed General MacArthur, who was a major general in the war, to be the Governor General of Japan. And what he decided is the Japanese at that time, before the war, they were known for making very cheap products, but very low quality. And he realized it really needed the country to advance and go the opposite way. Very high quality, and because the country was devastated and they needed to revive the industry. So rather than do it the old way, they decided to do it the new way, the quality way, which is high quality, high price. So the idea here is the country switched. And in order to do that, he brought in Schuhart and Deming to teach quality to the Japanese industry. That's in the 1950s, late 40s, 50s. So Japan was so appreciative of what Schuhart has done and what Deming has done that they have a quality prize called the Deming Prize, because Deming introduced quality to the Japanese culture, and they took it very well. So Deming was one of the giants of quality, and I had the pleasure of meeting him when I was in the industrial technology department at UMass Lowell. We invited him to speak to the university. He came in, he was in his 90s. Most of these quality people were in their 90s before they passed on. And he gave a speech at the big lecture hall there in Ball, and you could hear a pin drop when he spoke. He talked about quality. It was absolutely fantastic to hear a legend and then hear him in person. So, so that was the beginning of the quality revolution. Now, fast forward, so Japan adopted that quality policy. We kind of abandoned it until the 1970s. What happened in the 1970s? The 1970s was the oil crisis. So there were two oil crises in the 1970s. One in 1973, and the other one, that was a war in the Middle East, and they had an oil embargo. And then again in 1978, when OPEC was a monopoly and they wanted to raise the price. So what happened is American cars were gas guzzlers at that time, and with the embargo, we had no oil. So people were lining up in the streets, pushing their cars as they ran out of gas into the gas stations. Well, what they discovered that the Japanese imports and the German imports, like a Volkswagen, had much better gas mileage. So they bought Japanese and German cars. They bought these cars. And what they discovered to their pleasure, not only they had better gas mileage, but they also had much higher quality. American automobile manufacturers, which owned 100% of the market, had a philosophy or strategy of planned obsolescence. The idea is you have your car, you run it for 3 years, 100,000 miles, and you buy a new car. That's the way they train the customers. So the Japanese broke that, and the early Toyota commercials would have people driving Toyotas for 10 years and say, I've run it for 300,000 miles, I've run it for 500,000 miles. So they kind of broke that issue. So all of a sudden, this country, the United States, which started quality, again found itself completely behind the quality curve. And there was a scramble to get quality back in. So many quality gurus came in at that time. Some of the names, somebody like Juran, who came up with the idea of a Pareto diagram. Pareto diagram is kind of a diagram that prioritizes or ranks the defects the quality problem. So you work on the toughest problem and then you work on the next problem. Of course, we talked about Deming and his DIMIAC plan. Then there was Ishikawa, a Japanese fellow, and he came up with the idea of the Ishikawa diagram. The Ishikawa diagram is kind of the best way I can say it is a qualitative way of solving quality problems as opposed to a quantitative way. So the idea then is you look at the causes of quality in a tree diagram. Sometimes it's called a fishbone diagram or a tree diagram or a 4M. You know, are the causes men, not anymore, are the causes folks or people, men, materials, machines. So these are the 4Ms that they have. Sometimes they added another one, it's called the 5M diagram. So the idea here is think about all the possible causes, how they connect to each other, and then start to kind of quantitatively, with a team effort, try to find out what the cause of the quality is. I'm not going to teach these principles because these principles you can read yourself. And when I had a class, I would assign different students to take one of these quality tools and talk about them. So I'm not going to ask you to or examine, have you have a question, an exam, or homework, because I believe you as graduate students, or at least this is a graduate course, you can read the material and figure out for yourself. It's fairly basic, so it's not a problem. It's mostly, as I said, qualitative instead of quantitative. Okay, the next one, of course, is Feigenbaum. Now, with Feigenbaum, again, I met him in a lecture, and he came up with the idea of TQM, which is essentially total quality management. So the idea of TQM is the idea that you organize yourself in a quality way. It's more of a higher level quality on the management side. So TQM was very, very popular in the 1980s. And then the last one is Crosby, who talked about quality as conformance to specifications. We're not trying, keep things the same. Design it well and then keep it level. That's the purpose of quality. That's at least the purpose of control charts. So these are the folks that really started the quality revolution. When we came back and we discovered that we really needed to understand quality one more time because we've forgotten about it in the 1970s and 1980s. The other thing that came out is the idea of Six Sigma. So where's the idea of Six Sigma came about? Well, one of the problems was TQM was the idea of constantly improving quality, constantly striving to improve quality. So when it got translated to this country, it got translated as zero defects. Well, it's almost impossible. Zero defects is an impossible goal. It's a goal meant to be broken. You can have perfect quality for a while, and then you have one defect, and then what happens? So companies in the U.S., at least the U.S. majority, began to think about quality in terms of a mathematical approach to quality as opposed to a qualitative approach to quality. So, and American companies were getting wiped out by the Japanese competition. So the Japanese companies started to take greater and greater market shares in cars. Then they moved on to electronics. So they were making memory chips and things like that. And I remember I was an engineer in a major electronics company in the US, and we did a study. We put in integrated circuits or chips from US suppliers like Intel, Texas Instruments, Motorola, and we compared them against Japanese suppliers like Sony and Fujitsu and companies like that. And the quality, we put stress testing on these components, and the quality in the Japanese was far superior. I was working at Hewlett-Packard at that time. And at that time, Hewlett-Packard bought 10% of the electronic components in the world. And they made a decision, the management made a decision, we're going to switch to Japanese components. That was a major, major crisis for the chip manufacturers in this country. So Motorola was the hardest hit, and they're the one that came up with the idea of Six Sigma. Now, I got interested in it very early, And luckily, I did meet some of the people that instituted. So the person that really started the whole idea was Robert Galvin. Bob Galvin was the CEO of Motorola. He was the son of the founder of Motorola. I met him in the 1980s. He actually came again to speak at the University of Lowell, Massachusetts Lowell, and they had a dinner for him, and I was invited to that dinner. We had a very wonderful conversation about quality and Six Sigma. Later on, I was invited to go to the company, and I met the actual engineer that kind of designed Six Sigma. His name is Bill Smith. He passed away only the last few years. And Bill Smith is the one that really put in the tenets of Six Sigma and what Six Sigma meant. And when I talk about Six Sigma, I'll talk about the conversations that I had with both Galvin and Bill Smith about Six Sigma. At that time, there was a lot of naysayers. And one of them was called Bob Smith, and he was saying Six Sigma is really, a total joke and not possible. The defect rate is so low, nobody can achieve that. So I arranged actually a discussion or a debate between Bill Smith of Motorola and Bob Smith, who was an independent consultant trying to make a name of himself as anti-Six Sigma. You might Google all the stuff. The meeting occurred, I believe, in Tennessee, in the ASQC, the American Society of Quality Control in Tennessee, and they had a back and forth argument. But it was very interesting because I was the one that set that up. The one that followed Bill Smith was Michael Harry, and he wrote Michael Harry, and he wrote a very, very important paper that connected Schuhart's work, that's the control chart work, to the Six Sigma work. And we'll talk about that when we get to the time when we talk about Six Sigma. So I'm very, very lucky, really, to have met a lot of these people in Six Sigma. I taught Six Sigma all over the world, and I've also taught design of experiments all over the world. Design of experiments, of course, was really, its sources come this way. Xerox, again, just like Ford, had a large percentage, like American companies had 100% of the auto share of the world in the US, 100% of the market. Xerox had 100% of the market in copying machines. Then came along Japanese companies, and they were making copying machines. Even IBM made copying machines because the market was so huge at that time. So there was a fellow in Xerox who was the engineering manager, and he went to Japan to try to understand how come they did such a good job. Xerox machines copiers would jam, would have a lot of problems. Copiers from Japan would be no problem. So he got introduced to Taguchi, and Taguchi came up with the Taguchi method. So the Taguchi method is a way of doing design of experiments. He brought Taguchi to this country. And what happened is the auto industry set up a program by the suppliers of the auto industry, because the auto industry, again, started decentralizing and going to supply chain. And they called it American Supplier Institute. So the major players were Taguchi. Apparently, he's the one that started the whole Taguchi methods and design of experiments. Then there was Clausing. He's the Xerox manager that brought him to this country. Then there was a person by the name of Patki, Mahdav Patki, who was the AT&T. Remember, Schuhart worked for AT&T. He was the AT&T disciple of design of experiment. And I was the electronics disciple of the design of experiment. I did the first design of experiments major project in the electronics industry. And it really was a revolution at that time. I was able to take a defect rate of soldering operation, which is every electronics manufacturer has, and bring it down to Six Sigma levels. So it was really very interesting. So again, I know all these people very well. On my desk, I have pictures of me and Taguchi. Clausing became He was Tufts has a Gordon School, which is a school of management, and its origin is the Gordon Institute was set up by the fellow that managed uh, Analogic, which is the company that makes the airport scanners in Massachusetts. So he wanted to teach kind of engineering management. This is the degree that I have here at UMass Lowell. So the Gordon Institute did well till Analogic wasn't doing so that well. So they sold the Gordon Institute to Tufts University. So, and they have an engineering management degree like we have an engineering management degree. So I know most of the people, the original people in Tufts and the Gordon Institute. So the fellow that owned that the CEO of Gordon Institute actually owned it. He brought in Clausing. Clausing is a guy that is from Xerox that brought in Taguchi here and made and funded him to be a professor at MIT. So I knew Clausing very well. I knew Taguchi very well. The other thing which is very interesting is when Taguchi came to this country, his English was not that great. So at that time, the internet was still in its early start in this country, and there wasn't any online courses or anything like that, but they did have video courses. So the idea here is Taguchi would record a video session, and then we will distribute the video to major institutions and companies in this country. Because his English was so bad, they needed folks to translate, to answer students' questions. So it's very interesting. I was a fairly young professor here, and I'm very proud to have been selected as the person for the East Coast to answer students' questions for Taguchi's video courses. And the fellow that was on the West Coast was another design of experiment guy by the name of Robert Montgomery, who's written a lot of books on design of experiments. And he really didn't like that because he's been around for a long time. He was actually recruited from Georgia Tech to University of Arizona. And he didn't like that an upstart like myself was equal to him in terms of recognition by Taguchi. So that was a very interesting session. So anyway, so I've been with all the big names in quality and in design of experiments. And I'm very, very proud to bring all that experience and knowledge that I have and share it with you in this course. So that's really what I wanted to say about kind of the origins of quality. And I'm trying to distill all this in 2 courses. So I have a course in design of experiments because it's really fairly complex. And you couldn't do it as a part of a course. It really needs its own course. That's a mechanical engineering 575. And the course this course would be everything else in quality in Six Sigma that's there. So between the 2 courses, I think you'll have a fairly good knowledge of Six Sigma. So it's very interesting that the auto industry, again, which was really hit hard by the Japanese quality revolution and kept losing market share, decided to have a standard, which they called at that time QS 9000. It has a different name. It's not ISO 9000. ISO 9000 is something else. It's a quality process for developing products or for running operation. QS 9000 is for designing new products. And they put all the tools together in QS 9000. So I was one of the teachers of QS 9000 around the country. So what I try to do in this course is to put in all the stuff that when I used to teach ISO 9000s to companies, it put in all the information in this course. So I've written a book on Six Sigma. I wrote it fairly quickly. So it's not a course book. It's the course book for this course, but it's voluntary because it's an old book. I mean, Six Sigma has been around for a while, and I wrote the book like, I don't know, quite a while ago. So so what I'm going to say is you don't need to buy the book. I don't know if it's still in print or not, but sometimes the publisher, because it's not selling that much, the publisher raises the prices. So I think it's like $200. I don't want you to spend $200. So I have essentially the book as notes for the course, as lecture notes for the course. So you don't have to buy a book. You can you can just use the course notes for it. If you buy the book, that's fine. I'm not going to make a lot of money out of it. I'll probably make about a McDonald's breakfast for each book you buy. So don't buy the book. All the book is in your class notes. Okay, good. So here's the syllabus for the course. And again, the way we're going to do it is this is going to be all on Blackboard. And I'll put in, when I finish this one, I'll make it into a video. And you'll see a YouTube video in the week folder. And then what we'll do is we'll have these recordings substituting for the first hour of the course. So you can watch them anytime during the week. Every week opens up on Monday. So you can watch them on before the course. The course is on Tuesdays, so you can watch them like 6:30 to 7:30 before the course starts. And then we have an engagement session, which is 7:30 to, I don't know, to 8:30. I don't think we're going to go up as high as 9:30. Usually students are pretty quiet. I mean, I'd encourage you to talk as much as you can, but you know, you do whatever you have to do. So, so I think we're going to probably finish about 8:15 on the session, although the schedule says 9:30. It says 9:30 because there's a half-hour break. There's not going to be any breaks. So it's really 9, and we'll probably finish about 8:15, okay? So again, I just talked about the course book here. This is the course book I was talking about, Six Sigma Electronics Design and Manufacturing. Unfortunately, there's the word electronics because my editor at McGraw-Hill was the electronics editor, and he kind of insisted on putting the word electronic in the title of the book, which really made me mad because we could have sold the book to a lot of people that are not in the electronics industry. Okay, so this is what we're going to cover, the syllabus. So you don't have to buy the book. The class notes are all in the weekly folders. Each week will come up every Monday morning, kind of Sunday, Monday, midnight. And then you can have all the notes you'll need. Plus, you'll have my lecture. They're going to be homework every week. So they're going to be a homework due this Sunday. Homeworks are due on Sunday. So this homework will be due on Sunday. So today's lecture is going to be process mapping. We'll talk about that in a minute. Then we go about 6 weeks, and then we have a midterm. So the first week is process mapping. The second week is FMEA, failure mode and effects analysis, and QLF is quality loss function. So quality loss function is really something that Taguchi came up with, which I'll talk about. Then we're going to talk about incoming inspection. So incoming inspection is a way of handling data. When you take data, you try to divide the data or separate the data from error to operators, if there's operators, if it's not automatic, if it's manual, and error due to the machinery or the equipment. So this is a statistical tool that we could use to do that in terms of parts between different. If you pick parts from suppliers to company or from company to another company, you really need to understand what GR and R are. We have a break on February 16th. That is President's Day week, so we're not going to meet that week. But I'd like the homework to still be due that Sunday because I like to be on top of it. So we're going to have it kind of front-loaded with a lot of homework in the beginning. And then so the first 3 weeks, kind of general quality topics. Then on the fourth, we get into Six Sigma. So I'll give you more about Six Sigma. The Six Sigma I teach is the original Six Sigma, which is what's called defect-based Six Sigma. It talks about quality defects. Today, Six Sigma has been watered down and called Lean Six Sigma. The idea of Lean Six Sigma is they're going to go back to the qualitative origin of quality and TQM, which is using these tools. I don't want to do that. If you're going to be a quality engineer, you're going to have to understand mathematically how to deal with defects through Six Sigma, through GR&R, through control charts. We're not going to be teaching you in a graduate course the tools we talked about, like Pareto, cause and effect, fishbone. We're not going to do that. So week 5 is the control charts, and that's what Schuhart told us. And week 6 is what I call process capability. So process capability is really at the heart of Six Sigma. And we will be doing things by hand, and then we have the midterm. We do not have a class doing the midterm. The midterm will be released. We'll have a week to do the midterm. The idea here is not for you to copy from each other. The idea here is for you to do a good job and not do a rush job. I trust you. This is a graduate class. I'm not going to worry about it. I want you to be responsible. You're going to be going to a company and you're going to be responsible for your own work. If you try to do it the easy way by working with other folks or by copying somebody else's, I'm very good at detecting that. So I'd like you not to do that. I'd like you to do the homework by yourself. Then what we're going to do in week 8 is we're going to go back and use Minitab. Minitab is a software, most common quality software, and it is we're going to redo everything we did by hand. We're going to really do it with Minitab. It's going to be a lot easier. Okay. Next one, week 9, is tolerance analysis, and this gets into systems. If you're going to be a systems engineer at one of the defense contractors, that's what you deal with. How do you handle tolerances? And then the idea is week 10 is the idea of process capability systems. So the idea here is to Six Sigma is done on the part level. How do you handle it at the system level? That's what week 10 is about. Then we have 2 weeks about DFM, design for manufacturing, another tool of TQM. And then there's a project. And also I'm going to have a guest speaker. I had a guest speaker 2 years ago because last year was already COVID. He's an excellent guest speaker. I can't find his video. They deleted it from Blackboard, so I'm going to keep looking for it. But we have the DIMIAC video, so that'll be good. And then the final. The final is going to be the last week of the course. Again, a 1-week course. So that's the course wrapped up in one. And then I'll give you other things about absences, discussion posts, assignments, midterm and final exams, how you'll be graded. There's 9 homeworks for 40%, 1 midterm for 25%, 1 DFM project 10%, and 1 final exam 25%, for a total of 100%. And these are the grades and the ranges that the graduate school recommends that you use. I'm not going to necessarily use those ranges. I might open them up depending how the class does. But I'm not, I might make an A- go from, because I'm going to have the A go from maybe 93 to 100. So maybe this one would be 89. I don't know. I can't guarantee it. It just depends what happens. I might go down one or 2 points to get these grades. This is a graduate course, and I understand we're supposed to, graduate courses, the average is supposed to be a minimum B, because if a graduate student gets less than a B, they get on probation. Now, at least the GPA drops below a 3.0, they get probation immediately. So we can't get B minuses in graduate school easily. But we also expectations of graduate students. All the homeworks have to be in on time, no late homework, no copying, things like that. So it's a two-way street, okay? I'm going to treat you as graduate students. I'm going to treat you as engineers, as adults, that you're true to your word, that you behave and act professionally, so that there is no copying and working together and things like that. The purpose here is to learn and to be successful. If a student just copies from other students, then you're not learning anything. Okay. Then the course description, and then guidelines for the homework. And then I have together on working together for assignments and exams. And you can read that policy. Okay. And what I try to do is divide up the exams into several versions, each version to be done, the version that matches your last digit. UML ID is the version you're trying to kind of, instead of all whatever students we have here, all 20 students work on one exam, I might have 10 or 20 exams. I might have specific exams for specific people. So I don't mind. I'm a very hard worker, so so I'll probably work as hard as you will on this course. Okay, so that summarizes the course, and I hope we have discussions when we have the engagement session on Tuesday starting at 7:30. Okay, so I'm going to close that and come up and start the session on the slides. I'm going to keep the slides like this. I'll make them a little bit bigger so you can see them. I'm going to have an introduction, which I already talked about a little bit, but I'll talk about it some more. Okay. Okay, so the idea, which is Crosby came up with, the Crosby I mentioned, conformance to specification, or Feigenbaum that talked about TQM, is the idea that quality, the cost of quality. What is the cost of quality? If you're testing something and repairing it, that's cost of quality. Anything that is not conformance to specification, anything that doesn't work it's supposed to do, that's quality. Things like inspection, warranty, scrap, rework. These are all easy to measure things in quality, and they are very expensive, okay? They are like 10% of the cost, 4 to 6% of the cost. The real cost is difficult to measure because you have setup and inventory, cycle time, things like that, which you don't want to do. Okay, so the reason they pushed for Six Sigma, Motorola said it cost them, COQ, cost of quality, it cost them in 1989 when they came up with Six Sigma, $1 billion. GE Aircraft cost them $500 million. So this is really what quality is all about, and what Six Sigma is all about. So Six Sigma, and that's according to Bill Smith, which I talked to myself. So this you're getting it from the horse's mouth. And it came out, they had a fake university, like Trump University. They wanted me to teach there. I didn't want to teach there. I love teaching here. Motorola University was a university that set up to teach Six Sigma. It doesn't exist anymore. So the idea here is to measure the way you do your business, whether yield increases in quality, whether reduction in cost, whether reducing inventory with just in time, whether number of models that you have to satisfy most customers, what is your lead time and response, if a customer wants a particular product, how do you respond to it? So they defined 3 classes. An average American company right here in the middle was growing at 10% per year. Great, but that's no big deal. I mean, a lot of times I came in because companies said, we want to be best in class. Best in class, the idea that they're growing 200% a year. Well, that's pretty fast. Then they're improving their quality by a factor of 2 every year, which is possible. And then world class is being the best in the world. So world class is like Six Sigma. The defect rate is 3 parts per million. If you do a million operation, your defect rate is 3 per million. So is that possible? I don't know. I mean, it's really more theoretical than, say, okay, you take the math and you extend the math to a million and see what happens. I mean, this is what we're going to spend the course understanding. When we say quality, Six Sigma quality is 3.4 parts per million, how's that? It's kind of not necessarily quantifiable. And that's what we're going to spend some of the course on. What is world-class behavior? It's like, okay, LL Bean, phone center, customer response center, order centers. Their goal was a customer calls in LL Bean and the phone gets picked up in 3 rings. No such thing as you call in to order whatever and then you wait and wait. No, 3 rings where they called. Whatever it took to have 3 rings for the customer, they would do. These are world-class quality standards, not just in production, not just in defects, but in all other measures. I mean, companies reduced their inventory by a huge amount using techniques of just-in-time. Company reduced their quality defects from parts per thousand to parts per million. Well, it's 1,000 times improvement in quality. It doesn't happen overnight. It's a systemic response. Here's a justification for Six Sigma. And the idea here is that most things we do in life is 4 Sigma, which is 1 in 10,000. Okay, a restaurant bill, writing a prescription, payroll processing. You certainly want your paycheck and payroll to be correct. So the reject rate on the average is 1 in 10,000. What Six Sigma was, as I said, is 3 ppm. I don't know if you can read that down there at the bottom. And the idea here is, yeah, I mean, the way you do it in industry before, if life is involved, is you do redundant systems. Landing gears in aircraft. Well, you have a hydraulic system, electrical system, and worst come to worst, a hand system, okay? So you have duplication, you have redundancy, power generation. You have redundancy in all these systems that are essential to life-sustaining medical products. But that quality is done through redundancy. We're talking about quality for a phone. A phone is not life-saving, well, maybe for you, but a phone, if you drop the phone, it means it still works. So that's the idea of best in class, the idea of Six Sigma, and the idea of defects in parts per million. I mean, I was a production supervisor, and I supervised 300 people. And typically, these folks were doing assembly operations. They were very good, and on the average, they would do 1 error in assembly every 200 operations. So what you do is you design the product so you don't make errors in assembly. We'll talk about that in DFM. So the best person I ever had, so the average was 200. There were operators that were doing 400, 1 in 400, and there was one person that was doing 1 in 1,000. The 1,000 operations, which are repetitive, very boring, hard to keep your concentration, he was doing it 1 in 1,000. So there's variability, and I think what we try to do is reduce that variability in the design of products, in the design of systems. And that's really what part of this course is all about. Okay, and one last slide about this is the study they did measuring, is quality transferable? So they measured Japanese performance in Japan versus Japanese performance when they brought their car factories in the US. So you could see the productivity is not the answer. I mean, labor is a very small part of the sale price of a car or the sale price of a phone. It's in a phone, it's like less than 1%. So it doesn't care. Nobody really cares if you spend a few minutes extra on it. But the defects, look at the defects, okay? Indeed, you can transfer quality from one factory to another. I'll talk about that when we talk about next week, when we talk about the quality loss function. Repair. Now look at the repair between Japanese in the US, Japanese in the US and Japan, or the US versus typical US cars, American manufacturer versus European manufacturers. The way the European manufacturers do is they have a lot of immigrants do their assembly, and what they do is what they have in lack of skills in the workforce, they do it through repair. So the repair area in a Mercedes or BMW, and I visited both plants, is about 4 times the repair area in a Japanese factory. Here's the other thing about inventory. Inventory, 0.2 days of inventory is kept versus 3 days. That's a 3 days versus 0.2 days. That's almost a 15 times decrease in inventory through just-in-time analysis. Most of the folks are in teams, and that's what really gives it. They work in teams, they rotate the job so they're not bored, and the result of it is much less, much better quality and much less boredom. Job classification, again, you could see very small number of job classification. Where you get into Europe and American factories, much greater job classification. You can't do this job if you're this level, if you're level 2, if you're a test technician, you can't do this. So it's a lot easier. And then tremendous amount of skill training for their employees. And employees are not bored, so they do come to work. And you can see it's about the absenteeism rate is 1/2 in the Japanese factory, either US or Japan, of typical American factory. And the answer is not automation. It's done by people. It's not done by automation. Well, I better get started since I already used up most of my hour. So what am I going to talk about today? What I'm going to talk about today is the idea of process mapping. So what's the idea of process mapping? The idea of process mapping is that you look at a system, you have inputs to the system, you have outputs to the system. The system consists of subsystems or sub areas or processes. So what you want to do is, if you're going to improve that system, if you're going to add quality to that system, if you want to add efficiency to that system, you need to describe that system in a way that is communicable. Okay, how does the purchasing department work? How does the manufacturing engineering department work? So we need to have a system of describing it. So process mapping came from software, came not from flow diagrams because they're too long. They came from kind of an upper level flow diagram. So this is what came in. It started in software quality and moved over to business quality. Okay, so a lot of businesses in medical, in finance, uses this idea of process mapping. The idea that you describe the operation of a process or a department in such a way that you can look at it and see if we can make it more efficient. So all I'm going to do is give you a homework in order for you to study it. Okay. So instead of flow diagrams or software, line by line flow diagram, we have a big picture, and the big picture is called, there's 4 elements to it. A big picture is called context diagram. So the context diagram is the top system level view of the picture. It shows essentially what I call the process map. What is it that you're going to analyze? And this is a graphic that describes a process, describes its input, and describes its output. Then what you do is you go into bigger layer. You take this big top level view and you break it down into individual layers called data flow diagrams. So we're only going to deal with context diagram and data flow diagram. I don't want to get into too much on it. I just want to give you that big view of it, and then if you ever run into it in a job, you can recognize it. So it's a system they use for finding efficiency in these different operations. Then there is things that says process specification, which is essentially the wording of how to describe the process. So for instance, the homework is going to be process specification, and I give you the context diagram, you have to give me the data flow diagram. And then the last but not least is the data dictionary. So which dictionary means exactly what that is. You define each data flow. Okay, so the idea here is you describe a process, what they call as is. This is the way the process is run. Okay, then you observe it and you make a data flow output, data data flow diagram output of it. And then you can begin to see if there's redundancies in the process or there's gaps in the process. So the timing is not exactly described. It doesn't show you the sequence like a software uh, uh, flow diagram would show, the if loops and the and loops and the for loops and all that. But it gives you a feeling of the internet connection of the company. Okay, so data flows are presented by labeled arrows, processes presented by a circle, and data stores are presented by lines. So essentially, you go into a process or a design or a company operation or department operation, you take a top view of it, and then you kind of go down in data flow diagrams up to a certain level. You don't go more than 3 levels because then it gets to be too complicated. And then tie in each level to the upper level. So you might have one process on the top, 3 processes on the next level down, and then each process next level down goes down, and you have more definition. And I'll show you that in a minute. So, so the structured analysis or process mapping is really these 3 things we talked about. Source or destination, which is a rectangle, a process, and then data flow. So now what you do is you have data stores. So the idea of data stores is places you keep the data. Okay? So the data flow in diagram. It's very hard to do on computer because things would be crossing each other. So the way they do to prevent crossing from each other, if a data flow diagram and you need data flow from different parts of the diagram, when you put a double line here in the open rectangle, then that tells you it's just a copy. It's the same data flow. It's somewhere else in the diagram. This is just to stop the diagram from being like a cobweb, so it allows you to do that. So what I want to do now is to give you an example, and from that example is the way I want you to do the homework. I'll show you the homework before I go. I'm not going to discuss the homework. I'll discuss it in the engagement session. So for instance, I was working in a medical company. So one of the competition came up with the idea of, we're going to warranty our product, warranty meaning we'll replace parts, we will fix it for 10 years if you buy our product. So the production support process. So essentially, I was given that task. What happens if our company goes for 10-year warranty? What is the effect? Well, how do you do that project? What I decided to do is to use process mapping because it's a good way of having a representative of each area. And we had regular meetings, and we decided to plot how we do and then show what the effect is on each part of the organization if we go to a 10-year plan. So this is a good way when you want to do internal examination of a process change or policy change. So the policy change to be done at that time was a 10-year warranty. So we had to examine how the company works in handling new parts. Because the biggest problem with a 10-year plan, warranty plan, is where you're going to get your parts. Parts get obsolete very quickly. So how do we handle that? How do we handle the part gets obsolete? What is the process that we go through? And that's what we want to plot. Now notice there is no data stores on the context diagram. There's only departments, inputs and outputs, and there's only data flow diagrams. There is no data stores. So there are names in here, and every name in the context diagram, which is the top level, has to be in the data flow diagram, which is the bottom level. Okay, so these are different, as you can expect. Suppliers, material engineering, which qualifies the part, production engineering, which puts the parts in production, specifications, which specify the product and the components, material control that handles. So this is the engineering side and the supply side, and this is the production side. Corporate parts center that stores the parts, accounting that keeps track of everything, production people, and then materials control. So essentially, you got the engineers on one side, and you got the manufacturing people on the other side. So this is the context diagram, and I'm going to give you that in the homework. So when you go and look at different parts of that context diagram, I went through 3 layers, one for each. So this is layer 0. Okay, so this is the first layer down from the context diagram. So what I have seen as data flow diagrams, every name up here should show up in the names down here. Now, this was a 6-month project, so you're not going to do that for homework. But the idea here is to give you some feeling of a project that was done at work. So M schedule is the master schedule. When you see a double line in the master schedule, then you know it exists somewhere else. There is where it also exists. Then the part data library. There's a data library on each part. It exists here, and it should exist somewhere else. There it is. So the idea here is to show you how different parts of the organization work together. So you have production engineering, which is here. You have materials engineering, which is here. And you have scheduling materials control, which is here. Suppliers are here, corporate parts center here, and specifications here. So materials controls have the job, when a part runs out in a 10-year cycle, especially in high tech, where parts only last 2 to 3 years, they need to qualify new parts. So we need to understand that process. We need to qualify the supplier. We need to qualify the parts. Okay, so somebody has to tell us that there's a part problem. If there's a part problem, we go to the part data library. We go and then see if we can qualify a supplier. If we don't have a supplier that's on hand right now, we qualify the supplier. And then once the supplier is qualified, the part is qualified, then we hand it over to material controls, and they enter the parts. They put the new parts in the master schedule, and they order it. So production engineering handles production problems. So you look at manufacturing problems, you look at engineering changes. That's their main job. So the main job of materials engineering is new parts or replacement parts, or maintain existing parts, and the main job of production engineering is to solve manufacturing problems. If the manufacturing problem is the part is obsolete or the part is not performing to specification, then we need new parts, a new vendor, a new supplier, and new parts. Then of course there's material controls, which deals with inventory of obsolete or new parts. So these are the different pieces. So this is the first level. Then we went down another level in 2 pieces. So one of them was materials engineering. So now this corner of materials engineering got blown up, so to speak, in the next level. So you do things like, you can see things here that weren't on the upper level, on the higher level. There's supplier visits, there's taking supplier data, there's taking supplier process documentation. You do an audit of the suppliers. Then once you approve the supplier, after you do the audit, then you put them in the list of approved suppliers. So you can see all of a sudden more new things show up that you didn't see in the upper level. So kind of as you go down the levels, you explore more and more details. And then this is production engineering. And of course, production engineering, one of the biggest things that they do is testing of the product, testing of the parts. So essentially, you begin to see test plans, calibration of the equipment, things you didn't see in the upper levels. My apologies. Okay, so I've gone to an hour, so I'm going to go a little bit over. It's not a problem. Okay, so So that's really what data flow diagrams is. I've tried to do different data flows in different companies. So for instance, in this particular case, I believe it was a local company, local communication companies, and they had a problem in terms of jobs and how the jobs progress through the floor. So I was asked to look into that problem and see if we can get a system by which, the first shift and the second shift and production control and scheduling can all communicate together. So, yes, you could solve that with a computer system, but that takes too long. So we came up with what we call a whiteboard system and or production plan board. So the idea here is we decided that the best way of communication between production control, the stock room, the first and second shift is to have this whiteboard, and the whiteboard would look like something like that, where you look at the jobs, you have a plan for every week. What is it that the first shift was going to do? What is it that the second shift was going to do? Are we ahead of schedule? Are we behind schedule? And that's the idea of position to plan. Are we ahead or behind? And this way, there's a priority how jobs are being picked. Because before, there was no system, and the second shift, because there's nobody around, they'll take the easiest jobs and look very productive. That's a typical problem of a multi-shift operation. Always friction between the different shifts because they grab the jobs that are easy to do and they do them. So we try to solve the problem by putting everybody together, and this was the whiteboard system that we came up with. If you're ahead of the plan, don't do the easy job, do the jobs that you're behind. So this way we have an even schedule. Okay, so this is another example of solving production problems using process mapping. So these are the issues, and I'm pretty much done. And what are the benefits? Okay, one benefit is you document the current process for a look for the new products. You train engineers because the nice thing about process mapping, if you look at it, engineers kind of tend to have fairly focused view of their own job and not really understand how the world around them works in a company. So that works out pretty well in terms of helping them understand how different departments operate. And the idea is to invite each area to define their role by the process mapping. So essentially, if you invite representative of these areas, they represent the area in terms of doing the process map of the overall process map of the factory. So the idea is, of course, the biggest thing is highlight efficiency, inefficiency, and bottlenecks, and you use that information to design a new system. It's kind of positive. Okay, so I'm a little bit over, but let me just give you a brief look at the homework. Let's see if we can find that. I should have had it ready, but I didn't. That's okay. There we are. Okay, there's process mapping. There's assignment number 1. And I'll just give you the partial solution. Okay, so what I'm going to do is I'm going to give you a partial solution let me just close that first. I'm going to give you a partial solution of the, okay, this one doesn't want to close because it wants me to save it. I don't want to save it. So there we are. And let me just go. So what I do is I give you three different context diagrams. I only want you to solve one. I don't want you to solve all three. Maybe what you could do is look at a closeness between the three problems and your last digit UML ID. Okay, so maybe say if you're 1, 2, 3, it's easy. You pick up 1. Maybe you do it on a 3. If 1, 2, 3, do 1, 2, 3. If it's 4, 5, 6, we'll do 1, 2, 3. If it's 6, 7, 8, do 1, 2, 3. Understand what I'm saying? Do it in a way so that not everybody do the same problem. So essentially, what I give you is a problem definition okay? And I give you the context diagram. So the idea here is, for instance, in the early days of the internet, the idea how to messaging was going through phone lines, and how do you charge for the messaging? So what you want to do is you want to read any verb in here. Anytime there's a verb, there's a process. Routing the messages, storing the messages, calculating the charges. So these are all processes that are going to go in your data flow diagram. So only I'm looking for one data flow diagram from this context diagram. So your data flow diagram will have to have the send computer, the receive computer, and the toll computer in it. And these are the things going to show up in your data flow diagram. But your phone toll charge will be, the process that you're going to expand. So that's the first problem. The second problem is the ATM process. So how does an ATM process works? You put in a deposit and you say, I'm depositing $1,000. Well, how do we know that is true? Maybe you made a mistake. So you need to have, essentially, you say, okay, I deposited $1,000. Then you get a receipt that says, okay, you deposited $1,000, but it's got to be verified sometimes. So deposit is added. That's a process. There's a file of unverified deposit. Well, that means there's a storage for unverified deposit. And then you check the unverified deposits. So this gives you an idea what processes and what storages are needed for the next level for the data flow diagram. And the last one is a gene machine, to where somebody would come in with a sample and they want to know what the genes are in the sample, what the sequence of the gene is. So again, this is, you look at the description, there is key in the information, synthesize the DNA, and store the DNA samples in the samples of nucleotides, okay? And then obtain the engineer's charge number and put a printout in the sample log. So all of these things are in the context diagram, and I want you to take the gene synthesis and put it and spread it to a data flow diagram. So I'll talk more about it on Tuesday in the afternoon, in the evening, starting at 7:30, and we'll go a little bit more into the homework. So hopefully this will be good for a start for the first week. And I thank you very much for watching it, and we'll see you on Tuesday nights. Good night.